Hello, everybody. The topic of today is how could you take different families of functions and apply transformations to force them to go through particular points. This is going to be really useful later on when we want the functions to control specific things, because we're going to really need the functions to go from one point to another point. And this is how to make them do what you want to do. So let's just go through a whole bunch of different transformations. So if I want to force a cube root function to go through the point 5, I could translate it, I could shift it around, or I could scale it vertically, or I could scale it horizontally. I think a good first step for all of these is just imagine, either in your mind or on paper, what do these functions look like? So here's cube root. Let's pretend this point up here is 5. Hold on, this is not a good drawing. Okay, this is slightly better. So here's one idea. If you know where the reference points are on your original family, then it's easy enough to think about how could you just shift the reference point to be from where it starts to where you want it to be. So here I've got a point at 1. If I shift it right by 4 and up by 4, now I know that point will end up here. So my transformed function would look something like this. What would that look like? So if I'm going to shift it right by 4, then I'll subtract 4 on the inside, because it's a horizontal transformation. Then I'll add 4 on the outside. So that equation works. Or I could choose this point at the origin and shift it right by 5, and then up by 5. In that case, we would have cube root x minus 5 plus 5. So both of these equations actually take a cube root and put it through that particular point. Somebody today was thinking about the problem numerically. They said, forget the graph. Let's think about it this way. If I plug in the point 5 for x, I want to get out the point 5 for y. So let's start by taking cube root and plug in 5 for x. Now let's force it to have the value I want. So I'm going to subtract cube root 5. So now it's 0. And then I'm going to add 5. So what does that look like as a function? I'll take my cube root, I'll subtract cube root 5 and add 5. So here would be the general function, and we know it works because if I plug in 5 here, these will make 0, and I'm left over with 5. So pause and think for a second, what kind of transformation have we done here? The key is that this entire thing is just a number, and it's happening on the outside. So this is what we'd get if we just vertically translated it as far as we wanted to get to the point 5. So I'm taking this point right here and I'm shifting it up by the right amount to hit there. It's a little bit easier to see if we write it this way. Cube root x, and I'm going to reverse the order of those two terms. So 5 minus cube root 5. So all three of these work just fine. And these are all translating. Let's think about dilating. Let's think about squishing or stretching. Okay, so if I was going to stretch it vertically, if I was going to dilate it vertically, it's like every y value in my curve is going to get multiplied by whatever my dilation amount is. So for example, if I had, here's cube root x, if I put 2 out in front here, that means everything's going to be twice as tall. It's going to, all the y values double. But the problem is I don't want to double my y values. I need to multiply them by whatever the right stretch amount is to reach here. So what's that going to be? Let's sketch in what we want it to look like. We want it to look something like this. And again, these arrows are meant to indicate that we are dilating. So I don't know what the right factor is. So when I don't know, let's give it a variable name like k, and then let's solve for k. So what I know is that if I plug in 5 to this equation, I want it to be true, because that's what it means to be a point on the curve. It means it makes your equation true. So let's plug in 5. And now I can solve for the value of k that would make it true. So I'll divide by cube root of 5 on both sides. And I've got k is 5 over cube root 5. So now I can rewrite my original equation as 5 over cube root 5 times cube root x. And again, you're thinking about this thing as a number that's just the magic right number for stretching this as far as it needs to go through that point. Okay, let's do another example. Let's dilate the 1 over x function to go through 5, 6. So again, just imagining it, looks something like this. 5, 6 is going to be somewhere over here. This time, let's do a horizontal dilation. So remember, horizontal dilation means that my x values are going to get stretched this way. So I want this point to stretch far enough that it reaches 5, 6. Okay, so how's that going to happen? Again, let's write in a number that would do the dilation we want. So this is on the inside of the function, so that's a horizontal dilation. But we don't know what number this would be. If k was equal to 2, that would be like actually squishing all the x coordinates by a factor of 2, so everything would get narrower towards the axis. If k was 1/2, that would be stretching it out by a factor of 2. We're going to solve for what value is going to make it do the right thing. So let's plug in 6 for my y coordinate. Let's plug in 5 for my x coordinate, and then let's solve for k. So here I get k is 1 over 30. So rewriting my original equation, I've got 1 over 1/30th x, which is a little bit silly to write. We could also write this as 30 over x like that. So either one of these would be good. Here, when we have it written on the inside, we're imagining a horizontal dilation by a factor of 30, horizontal dilation outward. When I write 30 up here, it feels like a vertical dilation because I'm sort of on the outside of the function. And that's like dilating it vertically up by a factor of 30. Either way, you can see that it works because if we plug in 5 for x, 30 divided by 5 obviously gives us a y value of 6. Same thing would happen here. If I plug in 5 for x, here I've got 5 divided by 30, and that would be 1/6, but then 1 divided by 1/6 gives us the 6. So that's the idea. The idea is imagine what you're trying to do, and then set up a variable for the dilation that or for the transformation you want. So it could be a dilation or it could be a translation, and then plug in values to solve for what you want.